One of the questions that people often have is, why do we need this Project Loom? And we've got all these systems around already. You've got reactive programming, asynchronous code. The problem with all of that is that it can be difficult to debug. If things go well, it's great. But if something goes wrong, it can be tricky. Now, the problem that we have, if you have one-to-one number of Java threads to platform threads, it doesn't really scale that well. So I've got a little demo that I want to write and show or run for you. And it looks like this. I've got here a many threads which starts with a normal cached thread pool. And the cached thread pool, what we're going to do is we're going to start a new thread. Well, we're going to submit a job, but we're going to start a new thread. We're going to have a slight delay here with the phaser. The phaser makes sure that we don't submit the jobs faster than we actually are starting them. And then we're going to wait for 10 days until it's done. Of course, not going to really wait 10 days. We're going to crash before we do. And so let's run it with a cached thread pool, and we'll see how many threads we can actually make like this. If you run it, it creates threads and creates threads and creates threads, and after some time, it will crash with an out-of-memory error. Now, when it creates these threads, it's actually creating platform threads, which means it's got threads on my Mac OS X I'm using here. So you can see around about 16,000 on this particular machine, it crashed. And if you run top, you should be able to see Java somewhere, and Java will have a very large number of threads. I know I need to make it a bit smaller. Fonts are too big, so you can't really see. How do we sort it? Let's sort by thread. There we go. So you see Java's created 16,384 threads. So you know that that's 2 to the power of 14 or something like that. 14, I think. So there's a limit as to how many platform threads we can start. And because of that limit, we have to resort to all sorts of tricks in order to scale our systems. And so what we're able to do with Project Loom is, all right, so let's run this code again, but this time with the Project Loom virtual thread pool. So this is now using the virtual thread executor. It's not really a thread pool because it doesn't actually keep the threads around, right? It doesn't do that. It just creates them, and then once you're done with them, it'll just throw them away again. But if you run this, hopefully it's not going to kill my machine again. I don't think that was Project Loom, although it might have been. You never know. It is a project, but you can see here that we are. Yeah, it's a lot faster. First of all, it's a lot faster. It's like 30 times fast or something like that. And you can see that the number of virtual threads that is being created is quite a bit more than what we had before. Before, we could only go up to about 16,000 threads, and then we got an out-of-memory error. And now it's going to go quite far. It's going to go to millions of threads. So that's a nice little demo, just to show you that all the things we knew before, that you can't make too many threads, all of those assumptions go away once you have these virtual threads. So it's got millions now, and I've got some programs with millions of virtual threads running at the same time. And what's nice about that is that every thread of execution is now goes in one direction. So it's a lot easier to understand what's going on if you get an exception. As you can see, we can have a lot of threads in a single virtual machine. The only real limit is going to be the amount of memory you've got. And Project Loom is supported, the virtual threads are supported by networking, by the concurrency classes that you find in Java Concurrent. And basically, anywhere where you're going to block a thread, they're going to be able to scale much better with virtual threads. So I've got a little example here, and I'm going to just go through it quickly just to show you sort of the idea of where this can be useful. Let's say I've got a web page server that requires 4 different steps. I need to first of all scan the request that comes in for search terms. Then I want to search the partner websites. I want to advertising link, and last collate from the partner websites and show the website. Now, we can reorder some of the steps without affecting the final result. For example, we can create the advertising links at any time, and we could, in parallel, start collating the results whilst we're searching and whilst we're getting some results. So we can reorder things to some extent, but there are 4 main steps here. This is the first one, sequentially going through everything. I'm first doing the first step, scanning for search terms, then iterating over the terms, which are search terms, and creating search results out of that, and then creating advertising links, and then lastly collating all the results with all the search results and producing a final result. And this is the simplest option of simply going from the front to the end. And I've given a time budget to each step, and this comes to 4.3 seconds. Now, it's just an arbitrary time, so don't get stuck on the actual time. Of course, it depends very much on the network latency. It depends on the other servers, how long they take to return, etc. So here's how to do it if you wanted to use a normal thread pool with a callable. And we might get better performance this way to some extent, because we will be able to do a search, and with the search we can at the same time already produce the advertising links, and hopefully they'll be a bit faster. And so this is the idea. I try to write it as similar as possible to the previous one, where we start with scan for search terms, we then do the actual searching inside a callable. So that's a callable over here. It's a Lambda creating a callable, and that's going to be submitted to an executor service, which is going to return a future of list of results. All right, and so that's happening in the background. In the meantime, we're doing the create advertiser links. So we're not really benefiting that much here. The only thing we're going to do is create the advertising links at the same time as doing the search. And you can see that the time goes down a little bit, the total time. 4.1 seconds. Before it was, what was it before? It was 4.3 seconds. So if we basically saved 0.2 seconds because the actual advertising links creation doesn't take that long. All right, then another way you could do it is with completable future. I'm going to show you the code. It is faster, but it's a lot more complicated. And we also have to then always think about whether we're going to use a CPU-based a pool or an IO-based pool. And obviously, when you're using completable future, you want to specify which thread pool you want to use, because depending on what you're doing, it's going to be better to use a CPU IO-bound a pool. So what I did was I drew an activity diagram just to illustrate what we're doing. So we are splitting off into 2 different paths: the advertising links and the search terms. And the search terms is going to have different searches on different partners. And each time the result comes in, we can immediately collate the results. And what we can do is to rewrite all of this as a bunch of computable futures. And you can see the code is fairly complex, because I have to wrap each of the individual steps inside a completable future. And so it carries on for a few pages. I won't go into the absolute details, but it does return faster. So we get down to 0.9 seconds, which is quite nice. But it does become complex to do it that way. So what if we simply made a new thread, a plain platform thread per task? And I predict that the code will be simpler than the computable future. Here what I did was it looks a little bit complex, but that's only because I put the thread MX bean around it so that I can see how many threads actually started. So I want to count how many threads are started in this code. And I'm creating a new thread that's going to create advertising links with the request, and then I'll start that thread, and then I create a collection of threads, which is going to be from the search terms. I'm going to create a stream I then map that each of the search terms into a new thread that's going to collate, first of all, search on partner sites and then collate the results. And so each of the individual tracks is going to be a separate thread that's going to be used. All right. And then we're going to return each thread, and that's going to be a list of threads. So I want to make sure that I'm completely done by the time I exit from this page, from this method. Otherwise, it's whenever you start something, it's best to either return a way that somebody can join it and wait for it to be done, or to be done before you exit. So here what we do is we join them all, and then we print how many threads we create. And we actually create 11 threads because that particular request had 10 different search terms. So we had 10 search terms, and we ended up with 11 threads, one for the advertising threads, and then 10 for each of the search terms and the searches and the collations. The time is pretty good though. And the actual code here, I would propose is a little bit simpler than doing it with the completable future. But it's not scalable, because even if I have one thread per client connection, that is too many. We shouldn't be constructing threads for a client connection, because as we saw, we are limited into how many threads we can have at the same time. There's a limit as to how many connections we can have, but it's in the millions. We can have millions of connections at the same time on one machine, but we can't have millions of platform threads or native threads at the same time. So this is where virtual threads come in. And virtual threads are, first of all, use a lot less memory. They typically less than 1 kilobyte. They are very fast to create. As you saw, they were constructed more quickly than with the platform threads. And you can make, I tried it out, you can make over 23 million virtual threads in 16 gigabytes of memory. So it's quite amazing how much you can actually make with that. And the way that they work is that the virtual threads are actually executed on carrier threads. The carrier threads are currently scheduled inside a fork join pool. So it's basically just a normal fork join pool, and the virtual threads are being scheduled inside that fork join pool. The carrier threads are by default daemon threads. That's just something to be aware of. And it's by default going to be the number of available processes is how many threads you can have as carrier threads. The number of threads used for carrier threads might increase temporarily due to something called the managed blocker, which I'll mention again in a little bit. And also, if your virtual thread ends up blocking, let's say, for example, you're waiting on a reentrant lock, or you're waiting on a network connection, or you're sleeping, then the virtual thread will actually be moved off the carrier thread and put into like suspended mode, and then another thread will be able to run on that carrier thread. And this is a way that the relatively few carrier threads can be used to run lots and lots of virtual threads. Now, a question I'm often asked about this is this like green threads? And when Java first came out, we had green threads, and with green threads, the idea was that we had a simulation of threads. The simulation of threads was being used. In other words, there was actually only one thread running the whole virtual machine, and the single native thread or platform thread would be used as a single carrier thread. And this changed after a while to a more preemptive mechanism where each Java thread would be run by a platform thread. And that is where you run into problems where if you have too many of these, you end up with an out-of-memory error. But this is a bit of a mix in between, because you've got not a one-to-one or a one or many-to-one, you've got a many-to-many. So your millions of virtual threads will be run on relatively few platform threads. Typically the number of available processes, the number you get on your machine. Now the available processes on my machine, I've got 8 cores and I've got hyper-threading, so this will actually return 16. So it's going to have 16 threads that are going to run typically these 23 million virtual threads, which most of them will just be blocked most of the time, so there's not much to do. They'll just wait for them to become unblocked and then do something with them. Okay, so that's all. Yes, I've got a little gift for you. So this is a link to a course that I wrote, which I think you'll find quite interesting. Data structures in Java. So grab that if you want. tinyurl.com/devoxx21. I was amazed that URL was available, but this expires in 40 minutes from now. So at 5 p.m. it expires, and once you've redeemed it, you can use it forever. But it's a little thank you for those of you who are in the live session, not just watching the recording. So thank you very much for joining. All right. So let's get back to the single-threaded renderer. If threads are unlimited and free, why don't we just create a new virtual thread for every task? And so this is how our single-threaded renderer looked. And let's switch to how we can do this with virtual threads. So first of all, it becomes a little bit more convenient. They've got a nice static method called start virtual thread. And you pass in a runnable, and it creates a virtual thread, and it also starts it. And then it returns it. We've got it then here. That's advertising thread. So whereas before, let's go back a few slides. Before we had to make a new thread and then say thread.start. Now we can do it in a single method. We can simply say thread.start virtual thread with the runnable. This is I really like this addition to Java. And then this also is more simple. We can again say thread.start virtual thread, where we collate the results off the search on partner site result. And that then gets put into a list. Oh, actually what I wanted to do here is you say it. I changed most of the place. With this one I somehow missed. So there we go. This is really on demand. It's the code slide changing. So that makes it two lists. So there you go. And then we can join these. We can join these over here and wait for them all to be done before we exit, just like the other ones as well. And again, the time is pretty good. And we can create virtual threads in separate ways. The first one is a static method called thread.start virtual thread with the runnable. We can also say thread.offVirtual, which gives us back a builder, and this builder can then be used to start a runnable. And this is quite a clever mechanism. And if you know the book Effective Java by Josh Bloch, Effective Java describes an idea of a polymorphic builder. Now, you probably all know the builder pattern. Well, this is the polymorphic builder. You've got a builder that is a superclass for both native or platform threads and virtual threads. And then when you say off virtual, you get back a subclass of that common builder. And so there are methods which are specific to virtual threads and others which are specific to platform threads. For example, with platform threads, you can specify a priority. You can specify that it's a daemon thread, whereas you cannot do that for a virtual thread. You can't make a daemon virtual thread. The virtual thread is actually running on daemon threads as platform threads by default, but the virtual threads are you can't set a priority, for example. And there are other things which are relevant for virtual threads, which are not relevant for platform threads. So this is it's a really nice design. If you get Project Loom, have a look at that. It's really interesting. And then you can also get an executor service. This is also quite handy. As I showed you already, the new virtual thread executor, which it's not a thread pool. It simply makes a new virtual thread, and then once you're done, it just disappears, gets garbage collected. But what's also nice about this design is that executor service itself has become auto-closable. So you can put it inside a try with resource, and the close then calls shutdown and await termination. So this is a very neat idea. I like it a lot. So using that approach, we can actually rewrite the code and make it even a bit easier. We can put a try and have a try with resource with our executor service main pool equals new virtual thread executor. It's not really a pool, right? Because they're not pooled, they're thrown away once they're done. But I'll just keep the name consistent. And then we submit the first job and the second job. And here we're going to make within the job new threads. And so instead of trying to reuse the main pool, we just make another one. It's free to make. It's almost free to make these new pools. They're extremely cheap, so we can make as many as you want, and you're not going to run out of resources like that. And you actually need to do that because otherwise, what's going to happen is you're going to submit two jobs. This main pool, second main pool submit, and then as soon as we've done that, we're going to shut down the pool, which means we won't actually be able to necessarily submit more jobs, and we can get rejected execution exceptions if we try to use main pool once we've started the shutdown procedure. That's also why we need to layer the try with resource, but it's easy to do, so there's no real reason not to do that. All right. Again, it's nice and fast. Now, Project Loom is still in the works. It is a project. Now, there are 4 different layers of releasing something in Java. The first thing is when it's just being released, right? It's a feature release and it's new there, it's there, and it's done. There's nothing else to say. All right, so the preview release is slightly different. If you have a preview, it is something which has to be supported by all the OpenJDK vendors, whether they want to or not. And examples of that are, for example, the records. Records were a preview release. Text blocks, the new switch step, these were preview releases. And preview releases are 99% done. And so that's the second level. It's almost done. It might still change, but it probably won't change that much. Then we've got experimental features. Experimental features like ZGC was experimental in Java 11, and now it's a proper release. Experimental is quite far done, but it's really not quite done yet. And I don't think that OpenJDK vendors are obligated to support experimental features. And then we have what's the other one? There's one which is I forgot the name now. I'll think of it in a moment. But it's really just they're trying something out. And for example, the Vector API and the non-volatile memory, these are new ideas that are in the works. They're not quite ready yet, and they'll probably change quite a lot. But a project like Project Loom is none of these. It is so far away from being done that you don't know when it's going to be done. So if you decide to use it, be aware that it might still change quite a lot. So you can actually get an advantage by using it on the current release. It's not a release; it's just a project. But you must just be aware that if you're using it, that it might still change quite a lot. And here's an example. Like a few versions ago, they had the idea of having a deadline with the virtual thread pool. So you could start a virtual thread executor with a timeout of when it should time out, which is, for example, instant now plus seconds 1. So it should only be around for 1 second. And the idea was then the virtual threads would be interrupted on the timeout, which means that inside, if you have a loop inside a virtual thread, you'd have to actually check regularly whether we've been interrupted or not. And or if you're sleeping, for example, then you'd be interrupted with an interrupted exception. And a good approach would then be to throw, for example, a cancellation exception to say that we've been interrupted. Now, there wasn't an easy way to know which task timed out. And so this is still really something that they're working on. And they've taken it out again in the current version of Project Loom, version 18. So this code actually wouldn't work. But here's the idea, is just to show you if I if I set my limit to 300 milliseconds, then I'm going to get a timeout exception here. Right, and I could, but as I said, this doesn't actually work anymore. But I think once they release it, they'll have it with something else. Now, I did mention earlier on that the fork join pool might end up with more thread than we expect. The default is that it's configured with a number of hardware threads in our system, and normally it's the fork join pool uses that many threads, but when we configure it with the desired parallelism. So we don't specify what the maximum threads is. I think you can nowadays specify it, but I've never actually used that in the real world. So you just say I want it for 16 threads, and then it tries to maintain that level of parallelism. And this means that if a thread blocks for a while, instead of just reducing your parallelism, they then increase the number of threads up to some limit in order to keep the number of active threads the same. And in Java 7, this is when the managed blocker was added and fork join pool was added, only the phaser had implemented the managed blocker. So if you had the phaser, then you could, and a thread would block inside a fork join thread, then it would actually create another thread up to some limit in order to keep the parallelism high. And in Java 8, they added computable future to also be a managed blocker. Java 9, process and submission publisher, also managed blockers. And then in Java 14, they did a big one. They updated the abstract queued synchronizer to be a managed blocker. And this automatically then includes the rented lock, rented read write lock, the count unlatch, the semaphore, because these are all based on the abstract queued synchronizer. And I've got a newsletter about the abstract queued synchronizer I wrote a couple of months ago. If you look at javaspecialists.eu, you'll find all my newsletters there. And then Java 17, they add the link transfer queue, which I don't think anybody uses, but it's there anyway. And synchronous queue, which is used inside only one place, I think, which is inside the cache thread pool. And in the cache thread pool, they never actually call any methods which will be blocking. So, well, they've done it. I'm not sure there's match point, but they've done it. In Project Loom, they also have selector impl as a managed blocker and object wait and the old IO. So why object wait? Well, the problem is that if you're blocking inside a rented lock, for example, Project Loom understands that, and it's well enough, and it's able to swap out that virtual thread and to swap in another virtual thread onto that carrier thread. But if you suspend a thread whilst holding a synchronized, and you're suspending it inside a native method, like what happens with object.wait, then it's not able to suspend that virtual thread and to put another thread in there. So what they do is they simply increase the number of threads in order to make it appear as if it is supported. That's at the moment. They do want to change that, but that's how it works for now. If we've got code that blocks a thread whilst inside a native method, especially, and especially whilst synchronizing, then ideally we want to move over to a different mechanism. But if we can't avoid it, we want to wrap our code inside a managed blocker. I'll show you how it's done with synchronize in a moment. Also, they've rewritten a lot of the Java IO, so the plain socket impl has been replaced with an IO socket impl. Similarly with the datagrams, and it still works, which I think is always amazing that they changed so much and it still works. So the synchronized wait is not fully compatible with Loom. Here, for example, I'm making 10,000 virtual threads, and they all are calling monitor.wait, and it will create quite a few. I think it does about 10 times the number of hardware threads, but at some point it's going to not be able to make any more because it simply runs out of carrier threads. And so be careful of this. rather replace your code with reentered block. And this is what the object wait looks like now. They check if the current thread is a virtual thread. If it is, then they say manage block. This is a method, a private a package, or a internal method for blocker, for manage blocker, and so it does the task of waiting inside that code. And then if it's an interrupted exception, we rethrow that. So this is how the wait works, and it might increase the number of threads this way. There's actually one little, I would call it a bug or inconsistency with how it used to work, that if you call stop on the thread, you're going to have a different exception coming back. So we have to be a bit careful, but we shouldn't be calling stop anyway, so that shouldn't be a problem. All right, so we might have to migrate our code from synchronized to reentered lock and stamped lock, especially if we're doing waiting inside your synchronized. And in both cases, the idioms are a lot more complicated, but it's more compatible with virtual threads. Another thing is that the biased locking is turned off now by default. This should not affect you if you're running on modern hardware. They added biased locking at some point for older hardware to make it fast. On my laptop, I actually, even though it's not that old, it's 1 year old, as you saw, it just crashed, just reset it about half an hour ago. But my laptop's not that old, but on my laptop, I can tell the difference between biased locking on and off, and it's a lot faster if it's on. But on my server, which is where I do my benchmarking, I can't tell any difference. So it really depends what you're running on. If you find that your system is running noticeably slower, once you go to Java 15, try turning biased locking on again, to say minus access current plus use biased locking, and if it's faster than it was before with it off, then you can report it. Most likely it will not be faster. It might be something else. And the biased locking will help you if, for example, you're doing lots of locking where you actually need it. So if you're, for example, using vector, and you don't actually need a vector because there's only ever one thread using it. You could use an array list, but you're using vector. Biased locking will make it be as fast as vector. Or if you're using buffer instead of string builder, string buffer synchronized and string builder is not synchronized. Again, it's going to be faster with it on some hardware, but not on other hardware. My prediction is that you will not notice it being off. And if you do, please report it. Rather, do not use thread local. That's a good rule generally. Virtual threads support thread local by default, but it's costly and it's better to turn them off. Simply say allow set thread locals false. It doesn't make sense because you're probably not going to be reusing the virtual threads. You just use them once and throw them away, and so they often don't make sense. And you can see if you turn it on, if you have it on by default, then you're going to have one instance of the simple date format. But if you make it off, allow set thread locals false, then we're going to have every time you call get, it's simply going to just call with initial again and make another instance. So it'll still work, but it'll be a new instance every time. All right, I'm running out of time, unfortunately, because of the little snafu early on. So I'm going to just get through this quickly. This is the thread state machine for normal Java Lang thread. So it's only 6 threads. It's really simple. And this is what it looks like for virtual threads. So it's way more complicated. I actually haven't checked it for about a year because it took me so much effort to get this first diagram. It's probably changed since then. But just want to show you that it's really complicated to get that, to understand how that works internally. Also, just because the threads are really cheap doesn't mean that everything else is cheap. And for example, if you use the normal streams like a buffered reader or a print stream, they're actually really expensive in terms of memory. I was quite shocked how much they use, and this is how much it uses at the moment. The print stream uses 17,000 bytes. The buffered reader uses 16,000 bytes, and the input stream reader uses 8,400 bytes. So it adds up really quickly, and this is all this empty space. It's all this buffering space. So be very careful of that. And it used to be slightly worse, 25,000 for the print stream, and they decreased it after one of the newsletters I wrote. So they realized it was too many. With all of these things, education is really the key. I've got a concurrency course if you're interested. I write a lot of articles about Java, which you can all get for free on my website, javaspecialists.eu. And don't forget to grab your gift, tinyurl.com/devoxx21.
Thank you, Heinz. Thank you for such interesting speech.